If someone gave you this terrible Sophie's choice, would you prefer to go blind or deaf? It's a horrible position to be put in, of course. And as a musician, you'd think that my choice would be obvious. But simply in terms of cortical real estate, the amount of brain matter devoted to vision and hearing, vision is the mogul and hearing is just a small-time landlord. By some estimates, nearly 80% of the brain is involved in seeing in some way. I'd probably choose to go deaf. We've evolved to trust our eyes implicitly. Seeing is believing, and we seem to experience the world as one continuous image. But different aspects of vision are processed by different parts of the brain. There's one section devoted to color, another to detecting edges, and a third to processing motion, and so on. We don't notice that our brains are taking the world apart and putting it back together again, filling in details where we can't see and making inferences about how things should look based on our past experience. The way that our brain sees is modular to a large extent, but our conscious experience seems to be coherent for the most part. How is this possible? To begin to answer this question, let's consider our eyes and what they do for us. Our eyes are the most expressive parts of our bodies. In a study of social interaction on the internet, Scandinavian neuroscientists found that people were more cruel to each other when their eyes were blacked out by a bar during a video conference than if any other facial feature was obscured. When only the eyes were visible and everything else was blacked out or blurred, cruel words were tempered. You can fall in love just by prolonging eye contact, and someone's unwelcome staring can make you immensely uncomfortable, even though it's not hurting you physically. Why? Arguably, olfaction is the most intimate sense, as we literally sample each other's chemistry through our noses. But it's the eyes that are the windows to the soul. A dog might whine and scratch and cuddle, but who can resist the powerful emotions that we attribute to its pleading eyes? Your eyeballs are actually categorized as brain matter, and the eye is the only part of the brain that we can see without surgical intervention. From the front, we can see the clear, bulging region called the cornea. We can also see the pupil, the round black circle in the center, as well as the surrounding whites of the eye or the sclera. Of course, the most prominent feature is the colored circular patch of tissue surrounding the pupil, the iris. Pigmentation within the iris gives the eyes their color, the lovely browns, blues, greens, and hazels that have inspired artists and poets for centuries. For possibly thousands of years, we've known that the size of the pupil can be an indicator of attraction. The larger his or her pupil, the more attractive your date thinks you are. When your body is preparing for romance, your autonomic nervous system engages, dilating your pupils as a result. And when someone finds us attractive, our own bodies return the favor. Unless, of course, the attention is unwanted. Historically, even in ancient times, extracts from the plant known as bella donna, from the Italian meaning beautiful woman, were used in eye drops to artificially dilate pupils to make women more attractive, despite the visual disturbances that long-term use of the poison can cause. Beauty in the eye of the beholder, to be sure. Moving inside the eye, we find a clear crystalline lens directly behind the pupil. The basic operation of the eye now becomes clear. Light from the environment enters the eye through the pupil and projects through the lens, much like a camera. In a classic camera, a small hole called an aperture allowed light to enter and pass through the lens, which then projected the image onto a film to be captured. The eye is conceptually similar in that the pupil acts as a camera aperture, allowing light to pass through the lens and onto the retina in the back of the eye. Within the retina are special cells called photoreceptors, and these cells are the first step in the brain's processing of vision. Like film in a camera, photoreceptors in the retina have the job of capturing the visual scene. But they do so much more than that. They must be able to capture a dynamic scene, one that is changing in real time as objects of interest or the viewer move about. They also have the monumental task of converting images into language that the brain understands. That language is a sequence of electrical impulses. So we can think of photoreceptors as analog to digital converters. The visual scene is out there in the real world, happening in real time, but our brains create a version of it, and that's our experience of the world. Photoreceptors process light passing through the pupil and lens, sending out a ticker tape of impulses to describe the scene. The brain's job is to synthesize all of this information, creating the cohesive, continuous visual scene that we experience. On closer inspection, the camera analogy for the eye starts to break down. In fact, one of the counterintuitive aspects of the eye is that, unlike a camera, the eye works best when it is moving. The photoreceptors of the retina, the light-sensitive cells responsible for converting light into neural signals, rapidly lose their responsiveness when activated by constant light. Inside the photoreceptors are molecules called photopigments that react to particles of light. In technical terms, the loss of light sensitivity of photoreceptors is called adaptation, because the eye adapts to what is constant in the visual scene. We're only interested in what's changing. We want to see the moving lion, not the standing tree. We imagine ourselves as able to hold a steady gaze, or to voluntarily dart our eyes in the quick, flitting eye movements known as saccades. But it turns out that even when our eyes feel stationary, they still make very, very small involuntary movements called microsaccades. These microsaccades allow our eyes, even when fixed on an object, to avoid the adaptation of our photoreceptors. Without these microsaccades, the visual image would fade out as the photoreceptors quickly lose their sensitivity. You can see this for yourself. Try closing one eye and fixing the gaze of your open eye on an object across the room. Now, if you're listening to this lecture while driving, please don't do this experiment. Now, using your finger, gently press the side of your open eye. If you can hold that position, you'll find that the image will quickly disappear. By pressing on your eye, you stopped the microsaccades needed to maintain your photoreceptors in a responsive state. They soon adapted, and the image was lost. Photoreceptors come in two types, called rods and cones, names which reflect their different physical appearances. Different forms, but also different functions. Cones are responsive to the range of wavelengths of light that we experience as different colors. Rods are minor players in color perception, but are much more sensitive to light, making them useful during the night. Cones are responsible for the high visual acuity we experience when we look directly at an object. That is, when we focus our gaze on something, light bouncing off the object passes through to a special region of the retina called the fovea. The fovea is like an island inhabited exclusively by 8 million or so cones. Surrounding our island of cones is the ocean of 120 million or so rods, which make up our peripheral vision. Rods are best at sensing ambient light levels, and they modulate the adaptation to light and dark that we experience when we enter or exit a dark movie theater, for example. Rods are also better motion detectors, which is why we notice brief movements out of the corners of our eyes. Pretty useful skill when your eye sockets are fixed on the front of your face. This sensitivity of the rods is why, when you want to see something very faint or far away, like stars in the night sky, you should look straight ahead, but focus your attention to your peripheral vision. You can detect fainter light from the corners of your eyes, but you need to direct your fovea to the part of the visual field that you want to see most clearly. You can't read using your rods, but you can detect the sly movements of a black cat. It's at the level of the retina where we find the first example of how the brain deconstructs the visual world into disparate components. Because the colors sensed by our cones and the brightness and motion are sensed by our rods are processed by different brain regions. The color-sensing cones come in 3 different types, and together they cover the visual color spectrum from violet-red to green to yellow, using trichromatic vision, like an old color TV. These 3 types of cones correspond to the wavelength of light to which they are most sensitive: short, medium, and long wavelengths. If these cones aren't working correctly, or if a person is born without a particular type of cone, then that person will lose sensitivity to the wavelength of light that makes up a certain color. This is exactly what happens in the most common type of inherited color blindness, called red-green color blindness. These individuals have trouble discriminating red and green colors because their medium and long wavelength cones don't function properly. The brain cannot perceive what the body cannot sense. But is it possible to improve human vision by altering the sensitivity of photoreceptors? This is exactly what the US military tried to do in the early days of the Second World War, prior to the development of night vision technology. Their goal was to enable soldiers to see infrared radiation, which has a wavelength that normally is too long, outside the normal range of sensitivity for our photoreceptors. In the 1940s, we already knew that photopigments within photoreceptors involved a derivative of vitamin A called retinal that comes from the food we eat. The hypothesis was that fully substituting an alternative vitamin A into the soldier's diet might shift their visual spectrum by altering the photopigments. Incredibly, the military researchers found that indeed, after several months, the soldiers' vision did change, and they could see longer wavelengths of light. Once our photoreceptors convert light signals into electrical impulses, the signals are sent out over cellular cables that come together and exit the back of the eye via the optic nerve. The optic nerve travels to a relay station in the middle part of the brain called the thalamus. And from the thalamus, visual information is then conveyed to the next higher center, the visual cortex, located in the back of the brain in your occipital lobe. But in the retina too, things are not what they seem. The part of the retina from which the cables exit creates a blind spot. We all walk around with a little part of our visual field that we can't see because there are no photoreceptors in the part of the retina that receives light from that region. But we don't notice this blind spot because our brains fill in the missing information. It seems to happen pre-attentively, that is, before we've decided where we will focus our attention, and it's likely related to the activity of photoreceptors next to the blind spot and the neurons that get that information higher up in the visual processing stream. However it works, though, it underscores an important concept about how our brains function. We take shortcuts, heuristics that we've evolved over many thousands of years so that we can access more information than our limited brains can process quickly. Perception of visual information, that is, the psychological experience of seeing, requires a functional visual cortex. As in many areas of neuroscience, the study of the effects of brain damage gives us insights into how the brain works. And this work also demonstrates how specific parts of the brain can be. Damage to one region might affect a particular ability, but leave many other skills intact. For example, a stroke in the front and left side of the brain can impair speech and paralyze the right side of the body. But the patient might still be able to read and write and remember and move the left side of his or her body. The outbreak of World War I produced large numbers of injured soldiers, including many brain damaged subjects who were seen by neurologists. It was from these soldiers that an Irish neurologist named Sir Gordon Holmes began correlating vision loss with damage to the brain. His technique was very simple. He asked each soldier to stare at a stationary point while he moved a small spot of light around in front of them, repeatedly asking them if they could see the light. A bit like those ubiquitous cell phone commercials in which the attendant asks, "Can you hear me now?" Testing many patients, Holmes could take note of where the blind spots occurred and look for patterns of blindness from similar patients. Holmes discovered that the blind spots in the soldiers' fields of view were opposite to the side of the brain where the damage was located. So, damage to the visual cortex in the left hemisphere resulted in a blind spot on the right side of the soldier's field of view. He also discovered that visual fields are not uniformly mapped onto the visual cortex. Rather, the center of the visual field, the fovea, was affected by damage to a larger portion of the visual cortex than peripheral parts of the visual field, where our vision is not as detailed. That is, more of our cortical real estate is devoted to information coming from the fovea than from the periphery. So any damage to the visual cortex is more likely to affect the fovea than the peripheral parts of our vision, even though in the outside world, what we see in the fovea is only a small part of the visual scene. You can see how small your fovea is by trying to read a sentence just outside of it. It's a very small proportion of the visual field. These observations are consistent with what we would expect given the neuroanatomy of the visual system. The optic nerves exiting the eyes do in fact cross before reaching the thalamus, directing visual information, say, from the left visual field, that is, to the left of your nose, to the right side of your brain. What's more, the exaggerated representation of the center of the visual field in the cortex shows that the brain places heavy emphasis on processing the visual information from the fovea, the area of the retina responsible for highest visual acuity with the highest concentration of cone photoreceptors. There were some patients, like Mr. X, who provided an even more bizarre view of the visual system. Mr. X took a bullet to the head, and the damage to his brain was limited to a portion of the visual cortex. As a result, he claimed that he couldn't see. No vision whatsoever. If you asked him how many fingers you were holding up, he'd look at you as though you didn't understand English. He couldn't see, so how could he possibly tell you the answer? But if you pressed him and asked him to guess, 9 times out of 10, he'd guess correctly. That's way better than chance. And even more eerily, if you threw a ball at him without warning, he'd catch it. So there was a part of his brain that could see. It just happened to be disconnected from his conscious experience of seeing. He didn't know that he could still see. How is this possible? Was he lying? Did he have ESP? It wasn't clairvoyance, I assure you, and he was as honest as your most trusted friend. Instead, Mr. X had blind sight, another example of the division of labor in the brain. The neural signals emanating from the retina by way of the optic nerve go to several parts of the brain before reaching the visual cortex. The brain is receiving visual input from the eyes, but the damage to the visual cortex makes that processing path a dead end. Other pathways in the brain for processing visual information are still intact in patients with blind sight, and while the person doesn't have the psychological experience of seeing, the visual information reaching the other parts of the brain can influence behavior. Visual information from the retina reaches a still functional part of the midbrain called the superior colliculus, known to be important for accurate eye movements and for coordinating hands with eyes. That's why Mr. X could still catch the ball. Even within the visual cortex, the act of interpreting visual signals is subdivided. The duties of processing vision are assigned to different columns of cells and to different regions. Yet we still see the world as coherent. How does this work? Decades of study have revealed that the visual cortex is a highly organized collection of cells that are tuned to specific features in a visual environment. The visual cortex is filled with feature detectors. We know about feature detectors from Nobel Prize-winning research conducted by David Hubel and Torsten Wiesel in the late 1950s and early 1960s. They placed narrow microelectrodes into the visual cortices of anesthetized cats and then showed the cats a variety of light patterns on a screen. Now, microelectrodes are like very fine needles, and they allow scientists to eavesdrop on the brain, listening in on the neurons as they communicate with each other. As the electrode is dropped down into the visual cortex, right next to a single neuron, the electrical discharges of that neuron can be measured, appearing as very brief spikes on a screen. In fact, you can even connect an amplifier and an audio speaker to the electrical equipment and hear the neuron's electrical impulses, which snap and pop like popcorn on the stove. In essence, the Hubel and Wiesel experiment was similar to Holmes's experiment with brain-damaged soldiers. They presented their cats with a variety of light patterns while measuring the activity of neurons in the visual cortex. Holmes asked his patients, "Can you see my light?" Hubel and Wiesel asked their cats' neurons if they could see the light, receiving a confirming yes response with the pops and snaps of electrical discharges. What Hubel and Wiesel discovered, along with subsequent work by many others, was a map of an incredible, organized city of visually responsive neurons in the visual cortex. The spatial layout of the map was very orderly, an array of columns side by side. By columns, I mean an orientation of related cells with related properties arranged from the surface of the cells moving deeper, layer upon layer into the brain, like stacks of ice cube trays. First, they found that the cells in a single column responded most vigorously to light patterns in the form of short line segments emanating from one spot in the cat's field of vision. The cells in a particular column specialized in detecting just one orientation for those line segments, for example, vertical, horizontal, or in some cases diagonal. Cells in other columns specialized in different line orientations. Second, they discovered that each column of cells exhibited a preference for a particular eye, which they termed ocular dominance. They found an alternating pattern of left eye dominance in which cells in those columns seemed to receive visual input predominantly from one eye or the other, but not from both. Third, they found that interrupting the orderly orientation and ocular dominance columns were groups of cells that responded best to color, not orientation. These concentrated cell assemblies were termed blobs. Yes, blobs, in part because of the type of dye that was used to map their locations. And it was later discovered that there are connections between the columns, neural bridges facilitating communication between neighboring neurons. The takeaway message here is that the visual system parses, deconstructs, and detects the components of a visual scene: movement, luminosity, position, orientation, and color. So the brain is picking things apart. But how and when does it put everything back together? We experience the visual world as coherent, not as a series of lines and separate colors and other aspects, even though the way that the brain processes vision is in fact modular. This is called the binding problem, and it cuts to the core of the intersection of neural physiology, cognition, and the philosophy of consciousness. How do we experience the world in a unitary way when our brain distributes tasks to different clumps of cells? In the cortex, visual information is passed in parallel in two main directions: up towards the top of the head to the parietal lobe, or over and down to the temporal lobe near our ears. These are known as the dorsal and ventral streams. Dorsal for back, because when we walked on all fours, the top of our heads was in the same plane as our backs. And ventral for tail, since the bottom of our head pointed to our tails, assuming we had any. These paths are also known as the where and what pathways. The dorsal stream is called the where pathway because it processes the position of objects in space and coordinates vision with action, like reaching or kicking a ball. The ventral stream is known as the what pathway because it recognizes objects, tapping into our memory to identify what it is that we are seeing. Brain damage that disrupts the dorsal and ventral streams produces some profound visual deficits, known as agnosias. With its Greek root gnosis, meaning knowledge, the term agnosia literally means without knowledge. Patients with visual agnosia are still able to see, but their visual perception is no longer integrated with the rest of the cortex, making it impossible for them to interpret what they are seeing. For example, damage to the dorsal stream, or the where pathway, causes a condition called hemispatial neglect, in which the patient ignores everything on one side of the visual field. These patients experience the world as if half of it has disappeared. They draw faces with features only on one side, a flower with only half of its petals, or a clock with all of the numbers squished into one half of the face. Other damage to the dorsal stream can result in the inability to perceive movement. Patients who have motion blindness accurately see stationary objects, but not objects in motion. So, coffee pouring into a mug appears frozen in space, with the cup going from empty to overfull in an instant. Or cars speeding down the street appear as snapshots. This disturbance can be particularly frightening. Imagine what it would be like to try to cross the street when the position of the car seems to change instantly from stopped at the intersection to passing right in front of you. In contrast, damage to the ventral stream causes impairment to the what pathway. These patients are unable to recognize and name everyday objects. Yes, we all experience some forgetfulness from time to time, but object agnosia is much more severe. An especially dramatic type of agnosia is prosopagnosia, an inability to recognize familiar faces, such as famous actors or politicians, and unfortunately family members and loved ones. It's as though every face you see is that of a stranger, someone you don't recognize. These patients then have to use non-facial cues like the tone of somebody's voice or their gait or some aspect of their clothing to tell their friends from their foes. And their disability underscores how important faces are in our social interactions and daily life. The binding problem is still an unsolved riddle of science, but what these cases of brain damage and the findings of brain research suggest is that seeing, as well as interpreting, thinking about, and recalling what we see are all essential elements of a highly organized, integrated system of component parts. It's a realization that's exciting and disturbing at the same time. A little like how a computer might feel if it were examining its own motherboard. What does it say about who we are? Could it be that this component structure is the case only with vision, where our brains are most interested in what's changing and we take snapshots of the world with each movement of our eyes? Surely hearing is different, since it's so closely tied to time. We need to integrate sounds over time in order to make sense of speech, for example. Is the brain less modular when it comes to hearing? Is the binding problem an issue in that sense? In the next lecture, we'll find out.